So for our project, we chose to string a slack line between two trees behind the dorms. And we had one member of our team stand directly in the middle of the slack line and eventually come to static equilibrium. We then analyzed the forces and solved for the tension forces. You can see in that diagram. The lens that we're going to use for this project is one of the dynamics lens. This is because we have an object in static equilibrium and we are analyzing the forces acting on him and the objects around him. So we've initially got the measurements of the height was 41 inches, the distance between trees was 33.3 feet. And then we have Paul's mass here at 70 kilograms. The height from where the slack line is attached to the ground is 41 inches, and the height from the bottom of the slack line when he's standing on it to the ground is 16 inches. So we have the force of gravity acting on Paul. And for each of the tension forces, we can break them into X and Y components. Okay, and because he's in static equilibrium, we know that the gravitational force is equal to the tension 2y plus tension 1y. And because he is directly in the middle of the slack line after we've measured it out, we know that those two tension forces are equal. So we have force of gravity equaling 2 tension 1y. When we solve for the force of gravity, (700 newtons). And when we plug that in over here, we have tension 1y equaling tension 2y, which each equal 350 newtons. Now that we know those equal 350 newtons, we can go into finding this angle theta. Which is going to be the same angle on each side because he's directly in the middle. So for finding theta, we're going to use this diagram up here. So we know that this height, 41 inches, and we know this height is 16 inches. So in order to find the height of from where the slack line attaches to the tree to the point, the bottom point of the slack line where Paul's standing, we're going to go 41 inches minus that 16 inches. And that comes out to be 25 inches, which when put into centimeters is going to end up being 63.5 centimeters or 0.635 meters. So that is this height right here. So then we also know the distance already because we know the total distance from this diagram up here, 32.33 feet. So the horizontal distance here to make up the rest of this right triangle, 199 inches, which converts into 0.505 meters.
So unfortunately, it is actually at this point in the video that we make a slight error in our calculations. 199 inches is 5.05 meters, not 0.505 meters as we did in the video. So slight error, but it caused a pretty significant change in our final solution and our calculations. So to find theta, we shall use the tan inverse of the opposite, which is 0.635 meters, over the adjacent, which is 5.05 meters. And we get that to come out to 7.2 degrees. So now, using this 7.2 degree triangle that we just solved for, we can now switch this focus away from the distances and actually plug in the forces acting on it. So we have the vertical component of tension, which we know to be 350 newtons, is the y component of this triangle, and then the force of tension is the hypotenuse of this triangle. So using that, we can come up with the equation sine 7.2 degrees equals 350 newtons over the force of tension. So now, solving for x right here, we get that the force of tension equals 350 newtons divided by sine 7.5, which goes to equal about 2,681 newtons. And that, ladies and gentlemen, is the force of tension on the slack lining system. Thank you very much.